Okay, guys, so this morning you guys are going to have a look at conservation of linear momentum, right? But in two dimensions today. Instead of yesterday, you guys would have seen just collisions that were occurring parallel or perpendicular to the Cartesian grid, right? Which means northeast, southwest. So this morning, things are going to be moving off at angles, and I think even this morning's lesson relative to yesterday is even more important to keep track of information. From the standpoint, you have things moving off at angles now, right? And there's just more information now, right? It's more representative of what you would actually see in a collision in real life, right? So um, you'll see here. I always start these momentum questions with or even the energy questions in general, right? Um, you always start with kind of a before something happens and after, right? And that allows me anyway to keep track of information, right, in a nice clear visual way. um, so when I'm referencing back to fill in numbers that I know where the information is going. Okay. And much like yesterday, we can also conserve kinetic energy for uh, elastic collisions, right? So the ones that look to be happening here in this particular question, right? Inelastic collisions, you remember yesterday, were collisions that hit and stick together, and then the masses move because energy is not conserved there. Okay, so what I've done here below is I've just tried to spell out, you know, a particular question, right? There's no words on it. It's just here is a generalization, right? Where we have mass 1 with a velocity 1 or speed 1. Now today, these are going to be a little bit more specific from the standpoint of velocities because we're going to have things moving off at angles, right? And so velocity I'll be able to use the word velocity today instead of speed. Okay, so M1 is moving, M2 is not. So you see that its velocity is 0. And so when we come down to look at, the momentum in the x direction initially, right? We can see that the only momentum that I see, and basically what's contributing the momentum to the entire system, is the motion of mass 1, right? Because mass 2, its velocity is 0, it's going to cancel out, does non-existent, right? And then after the collision, you're going to see that, and I'm still dealing with x, we're going to see mass 1 move off at some angle theta, right? And mass 2 is going to move off at some angle phi. Okay, so that's the distinction that we're going to make today. You have two different angles, right? And we label them theta and phi just to keep track of them, right? So again, it's just getting at the organization of the data that's given to you, okay? And then the other thing you can do is create a second statement, much like what we had with forces when you're solving for normal forces in order to solve for, let's say, the force of friction, right? In a particular question where there's a force being applied at an angle, we can look at the amount of momentum that's occurring in the y direction. That's what this second question or second line is looking at, right? And so we can see that initially, neither of those two masses have any momentum in the y direction, right? And remember yesterday that this indicates the equal sign, right? And so initially, over on this side, we have 0 momentum in the y direction. And then after, we can actually calculate, if provided the appropriate information, what the y components would be, right? You can see them just appear right here, right? And their corresponding masses and velocities after. Okay, so just a little bit more information today. But you can see we're just breaking, you can think of these as almost like a momentum, it's a momentum vector. And we break that momentum vector into its x and y components, okay? Just as we have done for the entirety of the course when dealing with components, okay? So you're going to have two x components. In this particular instance, both of these x components, here I'll change colors here, it's starting to get a bit messy. Both of these two components are acting in the positive x direction, right? So we see positive, positive come out in our x statement for momentum. And then in the y directions, you'll see that, okay, well, the momentum on mass 1, the vector for that is acting, I'm just going to erase everything. The momentum for the mass 1 is acting in the positive y direction. So we see that positive there, m1, v1. And the momentum for mass 2 in the y direction is acting in the negative direction, which is why we see the negative spit out. Okay? So again, it's just components. It's a momentum component, if you will. Okay? X and Y. Okay? So some steps for solving these problems, I've kind of like gone over them up top there, but we can take components of the momentum before the collision, and this will give you two statements for the initial momentum, right? So we're going to have momentum in the y direction and the x, right? Sometimes there won't be momentum in one particular direction initially, right? It's just the context of the question, right? Whether or not two things are moving at an angle initially. That's going to dictate whether or not you have components before the collision, right? And then we can take the components of the momentum after the collision, and this also gives you two statements for the final momentum, right? So I think anytime that you guys can create more statements allows you to solve for more variables, if you will, right? And you'll see that when you guys get into linear algebra and things are vectors in 3 space, like 3D, you can keep track of the x, y, z in terms of representations. You can solve for x, y, z if you have three equations, you can solve for 3 unknowns. If you have 4 equations, you can solve for 4 unknowns. All we're doing is just adding more and more information to represent the world around us. We still apply, you could solve those questions like a 3 equation, 3 unknown. You could solve that with substitution elimination. Okay, what linear algebra will do it. The foundation of linear algebra is substitution elimination, but it allows you to solve it much faster. Okay, for more complicated systems. So the more information you guys can create, I suppose my point is here, the more complex of a problem you can solve. Okay, so the more that you can extract and create or represent, I won't say create, represent about the problem, helps you solve it. Okay, so we're going to set the components equal to each other, okay, since the momentum is conserved, and then you can use this equality to solve for any unknowns. Okay, so we're just going to look at 2 examples here this morning, something quick and easy, and then not quick and easy, but two examples, and I've uploaded 4 examples for you guys to try as homework, and then I've also put the solutions up as well. Okay, so I want you guys to try the questions first, and then I'll upload the solutions. You would have seen yesterday as well. I would have put in you'll see the solutions for yesterday's homework questions up there now. Okay, so what we want to do here is just want to tackle this first question. Okay, we're going to have 2 automobiles collide in an intersection. Okay, one car of mass 1,400 kilograms, okay, is traveling 45 kilometers per hour south, and the other car of mass 1,300 kilograms is traveling 39 kilometers per hour east. Okay, if the cars have a complete inelastic collision, okay, so that means that they're going to stick together and move inelastic. I always think of I think the connection I made to remember this was like elastics kind of bounce or bouncy the rubber, and inelastic would just be the opposite of that. Okay, and so they're going to stick together here and move together after the collision. Right, so we know for an inelastic collision that kinetic energy is not conserved there, right? And so we're really just stuck using a momentum argument for this. We can't really do anything to solve for velocities or any sort of creative solutions using kinetic energy for this, right? Because it's not conserved. So we're going to have to use, we have one option, it's conservation of momentum for an inelastic collision, which we know would take the form. Well, let's draw our picture first, okay? So we're going to go like this. We're going to draw a car 1. We'll call it mass, the 1400 one we'll call M1. And the 1300 mass or kilogram car we'll call M2. Okay, so we know, I always just like drawing these pictures, right? We know M1 is moving directly south with a speed of 45 kilometers per hour. Okay, and its mass is, maybe I'll move this and just organize the information a little bit clearer. So M1's moving, and we can tell that if you guys draw your coordinate system, which you should always be doing, you know, your vector here indicates to me that it's traveling south, so you don't need to write the south here, but you can if you'd like. Mass 1 would be 1400 kilograms, okay? And these two, and this car collides with another car traveling directly east. M2, which was 1300 kilograms, and its velocity, or V2, was going to be 39 kilometers per hour east. Okay, and so here's your initial scenario, right? And then we're going to draw what would happen finally, right? So after the collision, well, after the collision, the two cars are going to become intertwined, and they're going to move off at some angle. It could even, maybe even, I don't know if it is going to let me rotate it. They're going to become intertwined and move off at some angle in this direction, right? But the word intertwined means that this is going to be M1 plus M2 now, right? So we know what the total mass is going to be. And the thing that we're looking for is this final velocity vector, right? So both magnitude and direction, though, is the catch. Okay? And so we just got to run through this. Well, we learned yesterday, just going to move this up. Just going to try and save some space here in case we need it. Okay, we learned yesterday how to write a momentum statement for an inelastic collision, right? I don't know what the angle is. We'll call it theta, okay? So what I think we can do here is we're going to write two statements, right? We're going to have momentum initially in the x direction, right? And we're going to have momentum initially in the y direction, right? So let's do that. So we're going to have, let's say, px. That has to equal, or I guess we're going to go initial, is all coming from the momentum in the x direction is all coming from this vehicle traveling in the east direction. Okay, and so we're going to have, well, m1 v1 doesn't have any momentum, so we're going to get 0 there, right? But maybe I'll write the statement out. m1 v1 plus m2 v2 has to equal, we're interested in finding what this component is, right? Because we're dealing in the x direction. So we want m1 plus m2 and multiplied by the final velocity cosine of theta. Okay. Now I already know, and you guys should be like thinking too, is like, oh, well, it looks like we have a good chunk of information, but there are two things that I'm going to be interested in looking for, right? I'm going to be looking for the final velocity and also this angle, right? So this is the trick with these questions, okay? It's just identifying some of the things that you're going to need to know. So then we could also look at the momentum in the y direction, right? And we're going to look at, okay, well, initially, maybe what I'll do here, I was trying to organize information. I'll take this and move this over here. We'll do these two things separately and see what happens, okay? So on this side, we'll do all the x stuff, okay? So in the y direction, we're just going to write the same statement, right? m1 v1 plus m2 v2 has to equal m1 plus m2 multiplied by vf, right? But this time, what am I interested in? This is my momentum in the y direction, right? I'm interested in finding this, the y component, which we know is going to be sine, right? And so I'm going to have the sine theta here on the end. Okay, and now we can just start running with this question and see where it takes us, right? So let's just go back to our x for a second. We know everything in the x direction in terms of where the momentum is coming from initially comes from mass 2, right? Because it's the one traveling in the east-west plane, right? In the x direction, right? So we know that m1 is not contributing anything to the x momentum, and so we're going to cross it out. It doesn't have any velocity in the x direction, right? So here's what we got for the x direction in terms of momentum, and the opposite is going to be true over for the y direction, right? m1 in the y direction is what's contributing all of the momentum in the y direction, but m2 is not doing anything, right? It doesn't have any velocity in the y direction, so that's where you're at. Okay, so let's just try plugging in some numbers and see what happens. Okay. Okay, let's do that. So m2, you guys know to be. I'm just going to substitute some numbers in. We need to multiply that by what its velocity is, 39, right? And that has to equal 1300 plus 1400. And then that's going to be multiplied against VF cosine theta. Okay, well, let's just throw in the numbers on the other side as well, right? So M1 is going to be 1400. We'll try to do these two things line by line. If we did these together, it might make a little bit more sense too. You can do whatever order you want, but 45 is going to equal to, again, the 1300 plus, oops, not multiplied, plus 1400 VF sine theta. Okay. So now we can just type into our calculator a little bit of work. Just gotta find my calculator. We can go 1300 times 39 should equal 50,700. Okay, and that's going to have to equal 2,700. 2,700 VF cosine theta. Okay, and then we can go. We'll go to the other side and just do the math there. 1,400 times 45 should be 63,000. Has to equal again the 2,700 VF sine theta. Okay, so now we're at a little bit of a fork in the road here, right? We're like, okay, well, it's a little tricky to solve this using your conventional like elimination from the standpoint that like everything looks like it lines up. The problem is if I were to move this down here and you were to add these two things together, I don't necessarily know what to do about this cosine and sine thing. Which leads me to think, okay, well let's try substitution instead and see what shakes out. Okay. So let's just I see one shared thing here between the two. I mean, there's a theta, and like, but are you going to rearrange for theta? Probably not. What I'm thinking is let's rearrange for VF somewhere and substitute whatever that is equal to. Doesn't matter what side you're equal to. Let's substitute it into the other equation and see what shakes out. Okay, so I don't know, let's solve for VF in the x direction, say. Okay, so let's say in the x direction, I could divide both sides by 2,700, right? If I were to, oh boy, 2,700. If I were to divide both sides by 2,700, these are going to cancel, and we're going to see VF is equal to, VF cos theta, I'll leave that there for a second, is equal to, let's do the math, 50,700 divided by 2,700, 18.77, call it 78, if we round. And then I can divide both sides by cosine theta. Okay, and that's going to cancel. And so we know what VF is equal to. It's 18.78 over cosine of theta. Now, this is okay. It's no different than having could be a y, basically, right? It's just a variable. Something we're trying to solve for. So let's plug that in there now. Well, we'll go over here and say 63,000, right? So I'm going to take this and I'm going to put it in for VF. That's what I'm going to do, okay? So 63,000 is equal to 2,700 multiplied by, well, what's VF equal to? 18.78 over cosine of theta, sine theta. Okay, and then we're going to say, okay, let's go, we're just got to deal with the fractions here, right? Well, this is over 1, and this is over 1. So what are we going to do? How do we multiply fractions? Well, we multiply all the tops together, and we multiply all the bottoms together. And what are we going to get? Well, we get 63,000 is equal to 2,700 times 18.78 is 50,706. And then that's going to be sine theta, all divided by cosine theta. Well, this should look familiar to you guys. Sine theta over cosine theta. Right? You guys know that should be 63,000 is equal to 50,706 tan theta. All right? Sine over cos is tan theta. And then we can say, okay, well, let's just divide both sides by the 50,706, and we'll see tan theta is equal to 63,000 divided by 50,706 is 1.24. And so you're going to find that theta should equal, if we go inverse of that, 51.17 degrees. Okay, that's what theta is equal to. Now that's just a part of the velocity, right? Now you guys know that, okay, well, I found what theta was. I can take theta and put it in over here. It's going to spit out what VF is. No problem. You're all done. Right? So VF is going to be equal, the final velocity is going to be equal to 18.78 divided by the cosine of 51.17. So I'm going to go cosine of 51.17 gives me 0.62, and I'm going to go 18.78 divided by answer 29.95. And that's going to be kilometers per hour. All right. So all we have to do now, I'm going to use this little space up here. Okay. I'll just use this up here. We just got to write out our final velocity vector, right? Well, we know we're going to draw, we know that VF, the magnitude of the velocity is going to be 29.95 kilometers per hour. And then the car was traveling east 51.17 degrees south. And that's your answer. Okay? It's a little bit like, that's a cool question. There's a lot in there. But again, it just gets at the fact, like, it doesn't matter what it is you're solving for. You just identify the two things that you don't know. Or again, it comes down to the basics of, like, let me see this with the grade 11 questions. It's identifying what you know and what you don't know. Okay? And the free body diagram or the picture or whatever that you guys use, the grass method, whatever helps you identify those things, makes solving the questions easier. Okay, I knew as soon as we plugged in there, VF cos theta, there's two things there that I don't know. But I have the momentum, I have two equations, basically. I've created two equations, right? I created two equations here and here. So I can use those two equations to solve that problem. Okay? Now, something like the next question, those do take a little bit of time. Okay? So something like the next question, we're going to look, that was obviously an inelastic collision. I want to show you an elastic collision too, right? So in a game of marbles, a collision occurs between two marbles of equal mass. Okay? And one marble is initially at rest, and then after the collision, the marble acquires a velocity of 1.1 meters per second at an angle of 40 degrees from the original direction of motion, which would have probably been the horizontal. We'll draw the picture and make sense of everything. And then the other marble had a speed of 1.36 meters per second after the collision. What was the initial speed of the moving marble? Okay, so we're looking basically for the how is this whole system attained all this information, right? So we're looking for the initial speed of the moving marble, right? The one that contributed all this momentum to this entire system. Okay, and so what we can do, we can draw. Well, what's interesting about this question is that they've said that they're equal mass. Okay, so you only have one mass. That kind of simplifies things. Okay, or one numerical value of the mass anyway, right? So we could say, okay, well, let's again, we'll draw our diagram, right? We have a mass, and it's moving, right? It's contributing all the momentum. We'll call it V1. And it collides with, or is going to collide with, a second mass of equal mass, or second marble, I suppose, whose velocity, V2, is equal to 0. After the collision, right? After the collision, I want to draw a dash line. One of these marbles moves in this direction, right? At some angle theta. We'll just write everything generically. This would be a mass, and one of them has a velocity of 1.1 meters per second, right? And the other one moves off in another angle. They're not necessarily 90, but we'll call this angle phi, so theta and phi, right? And it didn't tell us the angle for that one, what phi was. We can say 1.36 meters per second here, okay? Okay, so now we can just write out our statement. Okay, or two statements, sorry, not just one, because it's happening in two directions now, right? And so we're going to have some momentum, right, in the x direction, right? And we're going to see, okay, well, initially, this mass here doesn't have any momentum, right? So we're just going to have mv1 on the left. And then that has to equal, and we'll do this question the same way, I suppose, too. We'll do it in the, I'll split it up, where we do all the work for the x on the left and then all the work on the right for the y, okay? Afterwards, we're going to have some momentum from mv1 prime cosine theta. And then we're also going to have mv2 prime cosine of phi. Okay? And then, just let me move this over, we'll shrink it down, give ourselves some room. So there's all these information in the x. And I want to find, well, let's write a statement for the y as well. Right, so initially, nothing going on initially in the y direction. And then we can say, okay, well, equals, that's equal to 1 point, I'll write it generically. M1, same mass. MV1, you get used to writing things in a particular way, and then you just end up writing them. And then we have to add in the momentum from the one MV2 prime sine phi. Okay. So we could start plugging in information. I think I may have at an angle of 40 degrees. I just want to make sure I have this all set up right before we go further. I'm not 100% sure that we have two angles here, just based on the wording. At an angle of 40 degrees from the original direction of motion of the motion of the other marble. Okay. No, I think we're okay. I think there is still two angles. Okay, so it's pretty much the same question we just did, except that we have two mass, like two objects flying off. Okay. So we just need to start plugging in information. I think that helps sometimes too. And that's maybe where I'm stumbling here. Is we'll throw in what we know and see what's left. Okay, and see if we're in any trouble. Okay, so let's plug in. We don't know the mass, but here's something convenient. It looks like the mass is irrelevant here, right? It doesn't matter because I could factor it out. It's in two terms here. Oh, I didn't put a plus sign here. It's in two terms, and so I can cancel the mass out if I were to factor it, right? And so we can see that this right here, this initial velocity is what I'm interested in for the entire question. What's the initial speed? Not even the velocity. It's not a velocity because it doesn't have any direction, it's just speed. Okay, so we're looking for the initial speed of this marble before the collision. Okay, and so we're going to start plugging in information. We know V1 after, though. V1 after is going to be the 1.1 meters per second. So 1.1 cosine of 40 plus Well, we know the final velocity is going to be 1.36 cosine of phi. Okay, so a bit of a crossroads here. I don't know phi and I don't know v1, but that's okay. We have another equation over on the right, so let's just jump over there for a second, right? And this is me working through your thought, like I'm thinking through this question the same way you guys would, right? So let's jump over to the other side and just fill in some information and see what we got. Okay, same thing here. If I were to move one of these terms over to the other side, or even if you don't even have to do that, I would say there's a mass in both of these, right? I would say, okay, well, we can go 0 equals mass, factor out the mass, v1 prime sine theta plus v2 prime sine phi, right? If I were to divide both sides by m, it's gone, right? So we're left with 0 equals, let's just start filling in the numbers for what's left, right? v1 prime, again, we know is being, v1 is the 1.1. 1.1 sine of 40 plus v2 prime, v2 we know to be 1.36, right? And then sine phi. Well, I don't know phi, so that's okay though, right? Because now I can solve for what it is. So let's bring this term over. Oh, one sec, guys. Sorry, I missed one critical part to this question, and I caught it just now. The y component here for v2, got carried away, is minus. Okay, I caught that because I was going to get a negative number when I was taking the sine inverse. Okay, that's how I remembered that. So let's move this term to the other side. We'll deal with the minus. So when we do that, it becomes positive. So what you're going to get is 1.36 sine of phi is equal to 1.1 sine 40. Right? And we're going to get sine phi is equal to 1.1 sine of 40 divided by 1.36. Okay, so let's get a number here on the right side, and then we'll find the sine inverse, and everything will be fine and dandy. Okay, we should see 1.1 sine 40 should equal 0.7. I'm just trying to find my pencil. There it is. 1.7, this is sine phi, divided by 1.36. Oh, 0.7, not 1.7, 0.7. Right, and we're going to take that number and divide it by 1.36, 0.51. 52, we'll round it. Okay, and so theta, or phi, would be the sine inverse of that, right? And so phi is going to equal second function 31.3. Now, in terms of answering the question this time, right? Like this doesn't, we know about all the final information, right? We're using this to plug into here so that I can find what V1 is. And that's it, you're done. As soon as we do this, the question's over, right? We don't need, because we're asking about the speed of the object, we know its velocity is, well, it could be traveling in the east direction. You could make it a velocity, but it only asks for what the initial speed is, right? Because it's traveling horizontal or perpendicular to the Cartesian grid, right? And so we can go down here and say V1 is equal to 1.1 cosine of 40 plus 1.36 cosine 31.3. Right? And so we say, okay, well, let's just do the math on that. And we get a final number. You can type that all straight right into your calculator if you have a scientific. 1.1 cos of 40 plus 1.36 cosine 31.3. Should see 2, our answer. Okay, guys, this is 100% about organization of information, and I suppose what you saw, or what you would have like seen me stumble with there, is like you begin to question whether or not you've set this thing up correctly, because it seems like there's not enough information, or like you got to process it. It's at this stage here. You guys just sit and think for a sec, right? Have you set it up correctly? I know I missed a sign. That wasn't really that big of a deal in terms of the context. I was more worried about the fact I didn't know this and I didn't know this. But just keep in mind, anytime, like, you just have to have confidence in the fact that, like, anytime you have two unknowns, or what appear to be two unknowns, you've created two equations. That question is solvable. Okay? And I have to remind myself of that sometimes too, right? It's just sometimes you got to process, they switch which information it is you're actually solving for. Okay? That's it, right? It really comes honestly down to, let's organize information, right? What's happening in X, what's happening in Y, and be careful with this. I got lucky because I caught it with, I was going to get a negative number here, which wouldn't have given me a nice angle, right? That's how I caught that. Just be careful, pay attention. There are still vectors, and vectors come with components, okay? You got to pay attention to the direction in which those components are acting, okay? So again, I would have set up, I should have, maybe this is my fault, my own fault. I didn't set up a positive, negative, negative. I was never reminded. I never reminded myself of that. Okay, it just comes down to the importance of this. Okay, so that's that. That's collisions, both one-dimensional yesterday and two-dimensional today. They're kind of fun questions. They get a little bit more complicated, but they're not too bad, right? It's just, it honestly comes down to how you organize yourself. Okay, and I think this is the way to do it. Keep track of how the momentum is initially in the X and after, and how the momentum is in the Y before and after. Create two equations you can solve for any two unknowns. Okay. I think the only other thing that would change is if you had some motion in a Z direction, you could you just have momentum in the Z. You'd have three unknowns and three knowns and three unknowns. You could do that question too. I won't ask you that, but possible. Okay, that's what linear algebra is for. All right, so that's that. This afternoon we'll be looking at Hooke's law and energy created from springs. Okay, so that's that for the momentum piece of the unit, and we'll jump back and look at some energy and forces from springs. Okay, this afternoon.